is the different measurement techniques that are available for looking at performance. So, there's two kind of subdivisions here, and each one of these has two common ways of doing things. So one is how is a measurement obtained? How is the measurement triggered? One of these methods is called sampling. So this is an indirect method of measuring. You interrupt when a tool is measuring performance via this method, it will periodically sample the state of the program that's running. And so there's nothing internal. You don't modify the program that's running at all. It just periodically will interrupt it and check where it's at, and it can see where it's spending its time by looking at the program state at different intervals. So it's appropriately named sampling. So it can check the status of these hardware counter registers, for example, and other things. So this has advantages in that it has low overhead because you don't have to put anything in your code to do this measurement. Almost zero overhead involved with that. The other is instrumentation, and this is that you set sort of like the PAPI calls. You actually add code to the code you want to profile to specifically measure events that are happening in specific code blocks. So the nice thing there is that you have a very well-defined delimiting space where you're measuring what's going on in that specific part of your code. The bad thing is that you have sort of the equivalent of the Heisenberg uncertainty principle, right, where you're now perturbing the system by taking the measurement, and so you don't know. You won't get the exact answer as to the performance because there's some perturbation there. But you can get close enough to get, by doing it in a smart way, which we'll try to hopefully show you today, you can get the overhead low enough that the answer will be close enough to get you where you need to be. So then the other thing is whether you're doing sampling or instrumentation, what is it that you're doing with the data? How is it that you're tracking the measurements that you're making? And so one of these is profiling. Sometimes we use profiling kind of synonymous with performance analysis. But profiling specifically usually means that you're going to just get an average look at the performance of your code. So you have something that you're measuring, a specific part of your code, and then you're going to, over all the iterations of your code, you're going to sum these counters up, and then you're going to take the average of them, or just the total, just sum it and get the total number of events that happen throughout the total execution of your code. So in the end, you'll get sort of a flat profile of the code where you're lumping everything together and organizing it with respect to the context that you defined that you wanted to instrument and look at. Whereas tracing is you're going to do a time resolved measurement of the code. So you'll take very fine snapshots of the code at very fine time intervals, and you'll actually be able to watch how the performance of your code is changing over time and look at specific iterations, specific events, and not just look at it as an aggregate or an average. So obviously tracing gives you the most detail, but so that can be a benefit or it can be a drawback, both in terms of having enough space to store it and also being able to make sense of what you get back. So we'll hit all these things a little bit in detail as we go through here. And then I think this is the last background we have. We talk about inclusive and exclusive measurements. So what we're talking about is the performance with respect to a certain region of the code. So the exclusive measurement would be, for example, only the time spent within a specific function. So not counting calls to any other functions that function might call. So you don't you're only measuring it when it's actually in the top level function. So for example, if this function foo calls two other functions, then the exclusive time, so the exclusive time is shown, so here in this orange you'd see these don't call any other functions, so all the time spent here is the exclusive time, well, sorry. So this is the time spent within this function foo itself, and then you have a call to bar, which you don't count if you're counting the exclusive time. But if you're counting the inclusive time, then you include the call to this child function in the total time. So so that's just a terminology thing, and sometimes you have to think about that a few times to get it straight. But basically, if you're looking at the inclusive time, you're just including everything that function calls. And by the way, feel free to pipe up with questions at your specific, your respective sites if you need clarification or anything is going too fast or whatnot. Okay, so as we take this, so that's enough of the background. As
we do have a question at Penn State. Excuse me.
Go ahead.
Hi, I'm a bit curious to know if these performance measuring techniques they work with other software interfaces with where we do not have access to source code.
If you don't have access to source code, so yes. So in that case, then you could do measurement via that sampling method that I mentioned. Okay, so and we'll show you some tools that will do that, wherever that was. Yeah. So with sampling, you don't need to change the source code at all. So you could have just a binary, and there's tools that can just interrupt the execution of that code and sample where it is and what it's doing at the time and the state of the system, and give you information. So yes, via the sampling, then you could measure performance without having access to source code. You obviously couldn't do that if you wanted to do instrumentation. Instrumentation, by definition, you're modifying the source code. Does that answer the question?
Yeah, thanks.
Okay.
We have another question from Penn State.
Sure.
I mean, you pointed out that there will be a overhead difference between the sampling and instrumentation. I was wondering if there is a difference in the accuracy of the results that you're collecting.
Yes. So so there's trade-offs there, and so with sampling, it's a little bit more fuzzy, and this is something that is also a little bit fuzzy to me. But with sampling, it's harder to tell exactly where you are in the code. For example, you can't. It only happens on, for example, I guess the finest resolution you could get would be like on a function level. So within a given function, where exactly are you, or can you do a measurement on a finer grain? You can't with sampling, because you can only access what is exposed to what the system can see when it interrupts, and it can see what function you're in and that sort of thing. But with instrumentation, you can actually delimit an exact place in the code where you want to measure specific types of events. And so you can drill down, like I said, with instrumentation, but you pay the price of overhead. So on both sides, there's these pros and cons, and you have to balance them. And we're gonna talk about when you might want to do these different types when you might want to use these different strategies for looking at the code. And we're not going to, again, it won't be comprehensive, but we'll give sort of a first cut at at where to use these different types of techniques. Is that clear?
Yes, thank you.
Great. Any other questions before we plow forward? Don't be shy, because most people have the same question if you have it. So. Okay. I'm glad we're getting questions. It keeps things more lively, so that's good. So what we're going to do is sort of take a journey, as I had mentioned at the beginning, through this process of performance engineering, hit some of these tools, but we're going to do it in the context of a real application that I worked with as part of this point project with a group that was developing their own code and ran into some performance problems, and we pulled out these tools to see if we could find where the problems were, and we did find the problems, and then they found a solution which was perfect. So we'll talk about that, and the code that I'll be talking about is called Unres. It's a molecular dynamics code. My background is molecular dynamics, and so hence this was assigned to me. So this is a code that they use to just to give you a little background is to study the process of protein folding. And so this code, sort of a couple of issues that will come up as we looking at the performance of this code, is that it's using a master worker type of a paradigm. So the process 0 executes along one path, and everything else executes along another path. If you're wondering what the heck this thing is, I came to know that this is Latin for like slave workhouse or something. So anyway, they were creative with the naming of their functions. So these are the workers here slaving away, and so this is the structure of the code, also this code ended up having a significant amount of setup time before you got to the real part that you're interested in, which was for molecular dynamics. There's a loop where you calculate all the forces between all the atoms in the system, and that's really the only thing that you're interested in as far as production code. But when it comes to doing experiments, analysis on a code, and you want to run a bunch of short runs, then the startup time can really get in the way, and it can obscure where the real performance issues are, because the startup time dominates the total execution time. And so we're going to talk about how to get around that too. So these things I think will be generally useful for different types of codes that will have similar issues. And even if your startup time isn't significant on 32 cores, if you try to scale to 100,000 cores and do performance analysis, or even 10,000, your startup time will eventually dominate if your code is scaling. So these things are useful. Okay, so here's the outline of the general procedure, and I have sort of divided it up into looking at the performance in serial and the performance in parallel. And also, just to be clear again on this whole thing, we're not talking about, in general, what you do with just your purely serial code that you never thought about parallelizing. In general, you're talking about, if you're talking about scaling to petascale, we're talking about a code that's been designed to scale efficiently in parallel, and we're just looking at the serial performance of that code. So running it on a single processor, although it's designed to run on thousands of processors. So looking at the performance of that parallel code in serial, and then looking at the performance of the parallel code in parallel. So we'll sort of go through this, and these two things sort of also go in parallel, looking at the overall serial and performance in serial, performance in parallel, looking at the functions where the code spends the most time, both when you run it in serial, and then also looking at where it spends the most time when you run it in parallel. And that's a key point, because where it spends the most time will change dramatically as you start to scale up by orders of magnitude. And so you need to make sure you catch functions that are not important when you run in serial, but become very important when you run in parallel.